The work that I'm presenting today is part of a larger research effort towards the development of improved assessment strategies for existing infrastructure. And the reason is that structures are not as strong as we would like. This is because of aging and deterioration effects. The fact that design and detailing was based on superseded codes, they're now considered old, and construction not always complied with the original design provisions. This leads to high maintenance costs, safety risks, and tragic consequences for the community, as in this case. So when we're dealing with a big infrastructure network, we have to identify priorities. And one of them is the case of half-joint bridges. You see a schematic on the screen on a Gerber system, and those joints have been widely used in the past because they facilitate construction. But there are a number of problems associated with it. One of them is leakage of contaminated water through the joint that promotes corrosion of the reinforcement, and also the fact that in the past the behavior of this joint was not fully understood, and this led to detailing that is not ideal. Now, most of the existing work on this joint focuses on the nib and the behavior at the re-entrant corner. But I think there's something that's been overlooked both in design and assessment, and it relates to the anchorage of the bottom bars. As you can see in the sketch, the difference, as we move away from the nib, it's often said that you move towards the behavior of a conventional deep beam. But the reality is that a normal beam sees the beneficial effects of external confinement from the support from the supports on the anchorage region of those bars. Whereas in a half joint, that zone is actually hanging, doesn't see that benefit from the support. This is the reason why it's particularly vulnerable to deterioration. And this is why we decided to zoom in and focus on the problem of bond and anchorage of corroded bars. So we try to develop a new approach for the assessment of bond, which is based on the splitting cracks. The problem of corrosion and bond has been studied in the past extensively. And you can group the existing studies in two main types. You have those who try to correlate the level of corrosion with the crack width that you see at the surface, and those who relate that corrosion level to the bond reduction. And some of them are remarkable, sophisticated, very, very complicated, but as you can see, there is sort of a scatter in the results. There is a lack of general applicability, if you want. And from an assessment perspective, you would have to use one model to try and predict the level of corrosion from the crack width that you measure from the outside, and then use that information to guess how much bond reduction you've got. And obviously, if there is uncertainty in each model, you're adding them up. Instead of adding complexity and adding more parameters to those models, we decided to step back and take a different perspective and focus on the fact that crack width could be a more effective and precise indicator of bond deterioration. And the reason for this, which is also a discussion of the results that we've got, is that when your steel bar corrodes, you have your parent metal that expands, so you have a volumetric expansion that you don't really control. You don't know how much they're expanding. Those corrosion products diffuse in the zone between the steel and the concrete, and you don't know how much of that rust is going in that void. You also don't know how much of that rust is going through the cracks, so it's getting diffused without developing expansive pressures. So we think that surface cracks, in a way, are a net measure of how much corrosion is giving you expansions and problems in terms of bond. And the other reason is that if you think about what happens at the interface on the image on the right-hand side, a splitting crack open, they push away this interface between steel and concrete, and they reduce the contact area between the two materials, reducing the load transfer that happens through interlock. And I find interesting that when we are talking about load transfer and interlock in the context of shear, it's kind of accepted that it's a function of the crack that's opening, but this hasn't made it through in the world of bond for some reason. I think it's because you have to move from a 2D planar problem, if you want, to an axisymmetric problem to understand how this works. So this is our first experimental program. We have generated corrosion in the lab. we've measured the splitting cracks at the surface, and then we've carried out bond tests. And what we have done in the accelerated corrosion bit, using an impressed current, we have sealed the specimens in different ways. And the objective was to generate the same amount of corrosion with different crack widths, or the other way around, if you want, the same crack width that it's generated by different corrosion levels. And we can group our results in three main types, if you want. You have the reference for the bars that are uncorroded that you see on the left, and then you have two types of behavior. If the cracks did not make it through all the way to the surface, you have a change in behavior, but your peak strength goes up. Whereas once you have fully developed your cracks and they reach the surface and you can measure them, you have a reduction in peak bond strength. And this is consistent with the existing results in the literature. So what you see here is on the top, you have the same plots that that I've shown before with existing results. And you see that we kind of managed to disrupt the conventional relationship. So we have levels of corrosion that are very high, up to 25%, with no crack width that you can measure on the surface. And at the same time, you have very high levels of corrosion that correspond to no bond reduction in the red plot, even increase in some cases. But if you plot the same results as a function of the crack width, there seems to be a better trend, if you want, a more accurate trend. And you can see that there are a lot of points that are sort of collapsed to the left-hand side of the graph. And these correspond to cases where corrosion has not generated pressures and crack width. And you can see that most of them, or the majority of them, are above 1, which means no reduction in peak bond strength. So this was promising. We think that there is something behind this that needs to be explored. But what about confinement? These were unconfined cylinders, and we know the real structures are different. There is stirrups, there is confinement, so the problem is much more complicated than this. So the second phase looked at the effect of internal and external confinement. And by internal, we mean reinforcement, whereas for external is the problem that we see in half joints, the fact that you may or may not have external pressure. So this is a problem that existed in bond test setup that are available in the literature, and we had to develop our own geometry, if you want. And you can see how it's very similar to half joint. We basically took what was the drawback of that joint, and we used it to better control the effect of confinement on our tests. So with this geometry, you don't have the parasitic effect of support pressures that a lot of authors have reported in the literature, and you can control how much stirrups you have in the transverse direction to see what the impact is on your bond behavior. So we've done a bunch of tests. We've tried different bars, different geometry, different covers, and in this case, I'm only showing a subset of our experiments. These relate only to one bar size, just to explain the trend. All the other experiments see a similar trend, show a similar trend. And what you see here fundamentally is that we have reduced the bottom cover to generate different cracking patterns and different crack widths, and to an extent also mimic the effect of complete spalling in the case of corrosion. You see that up to a certain point, there isn't really a trend. So even if your cover is much lower than design provisions, you're still able to generate significant residual bond strength. And we can compare results in a different way. So those points represent the peaks that you see on those curves, and they are plotted as a function of cover to diameter ratio, which is often the key parameter when you're dealing with unconfined concrete, because the resisting mechanism relies on a sleeve and thick wall cylinder analysis. But all those points don't seem to follow that trend. We were expecting a sort of shift upwards or a rotation due to the confinement of the stirrups, but we don't really see that. It's almost flat, if you want. And I think the idea is that the resisting mechanism is not relying on concrete anymore, because you have so much transverse reinforcement that is the one that it's providing restraint, as long as you have enough concrete to transfer those transverse pressures. And if we go back to the reinforcement layout of our specimen, which is similar to that of a half joint, I think it's clear this is telling us that that anchorage in that region is really relying on passing reinforcement and not on the concrete anymore. So there is more work to be done on this confinement conditions and on the role of splitting cracks, but I think we think we are on the right track. So to conclude, splitting cracks can be a better indicator of bond deterioration. We've validated this new bond test geometry and removed the parasitic effects from support pressure. Half joints do have low external confinement that may cause problems, but they have high internal confinement in that anchorage region that, on the other hand, is helping you. But definitely more research is required before we can derive predictive models that depend on bar sizes, cover, position, material properties, and transverse reinforcement. This is a case of a perhaps more elegant use of half joints at the bottom. And I'd just like to finish by thanking you and all the institutions that are funding us and supporting our research in this effort to make our infrastructure network more safe, resilient, and sustainable. Thank you very much.